What's up, everyone? Welcome back to Better Biomed. Today, we're going to be talking about digital circuitry and inputs and buttons and how you can measure what you measure where. Okay, if that makes any sense. We're going to talk about what happens when you press a button in a digital circuit. This is going to be really interesting. So this is based on digital logic circuits. And kind of like this microcontroller right here, believe it or not, the style right here. I know they're very small. And they're very small because that is the world that we live in. This right here, that little chip right there, that is the microcontroller. And this is a very generalized view of what's going on with these digital inputs. Now, one would think that when you flick on a button, that what's actually going on is you got 12 volts or 5 volts or 3 volts on one side of the button, you press the button, and that voltage goes into the pin and ta-da, activates something. That is not how digital circuitry works, okay? So what really happens is there are these things called pull-up resistors inside the semiconductors, inside the chips. And what is going on in here, you get this little resistor on each and every one of these, and you're activating them and you're pulling it up high. So when this button's not pressed, what we're actually seeing here is plus 3 volts, or maybe it's a 5-volt logic system, but I'm guessing plus 3 volts. And down here is what we're seeing on the outer ring. We're representing the ground. And I have some examples here. On PCBs, what you'll notice is you see how the corners here are copper colored? And often when you hold them up to a light, you'll see that there's this wide band around the edges and throughout most of the circuit board. That is called your ground plane. And it's normally an entire layer. Like these circuit boards are made for multiple layers. An entire layer on many of these boards is actually ground. And the reason they do that is for multiple reasons. One of them, because it's very easy and cheap to move the other side of the circuit all around the board. That's one reason. The other reason is by implementing ground as frequently as possible, you're minimizing the amount of noise and whatnot because ground neutralizes things out, right? So they have these large copper platens around the edge, and as much copper as possible will kind of dim out and reduce as much of that noise as possible. But anyway, the outside edge of this board, which you can see a lot of copper all over the place, and here near all the tie downs. So these are where the circuit board is going to be connected to a metal chassis someplace. And notice how they're all copper colored. And all of these ports right here are also ground. This one right here. All the shielding right here is all ground. And that's what we're representing on this outer circuit right here. This is ground. And it's connected to the same exact ground, usually, as the chips. So whether or not your chip is operating on 3 volts or 5 volts next to a 3 or 5 volt, you can normally tie into the same ground plane, which could be here, 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 here. Unless it's an isolated DC circuit, the ground plane is usually going to be the same, usually. And that means that I can hook up my reference point here off the shielding or over here. Or hell, I could even find one of the inputs like over here on the chip, because as you see, one of the inputs is going to be ground. How would I find that? Continuity mode on your multimeter, you hook one lead up to the shielding and you start running down the edge of the chip until you get the dee dee dee. And that is when you know you found the ground pin on your chip. All right, so here's what's going on. When you press a button, this wire is normally sitting high because of a pull-up resistor inside the chip. So what happens is when you push, you're bringing ground from here up, and it's going up to the pin, and it's going to turn this pin low. So it's called active low. And that means if you're checking to see if you have a signal on modern day digital circuitry, you would connect to your ground circuit. Let's go ahead and try with my multimeter right here. So I would put it on voltage. Of course, we are going to be on DC voltage. And I'm going to take my reference and I'm going to put it someplace on the ground plane. So on this one here, I would connect it maybe to shielding or something like that. And then I would measure on one side of a button. And if you see a positive signal there whatsoever when the button is pressed, then you know that you have a bad connection, probably at the button, because buttons are most likely going to fail unless you have a broken trace someplace. So that is how you would troubleshoot it, by depressing the button and then measuring to see if that 3 volt goes to 0. 0 means that it is actually activating, and that would infer that either the chip is defective or it's waiting on another condition before it does that function. So sometimes it does get the signal. So let's say that it's depressed. My 3 volts here goes to 0. So that means if I measure between this point right here, or the ground pin right here, to right here, and I'm getting 0 volts, that means that that button press is actually working. When you release the button, and this right here goes to 3 volts, now you know that that button is doing exactly what it was meant to do. Now, sometimes chips are waiting on multiple inputs in order to complete a function. So let's say up here, I have a limit switch. Or let's say maybe this one here is an interlock. Sometimes it's an intrusion switch or whatever. And maybe I'm waiting for this pin right here to also be an active low. But because I'm on my limit, so maybe it's normally closed, and when you hit the limit, then it goes open. So if I'm at my limit and now it's open, that means that this line right here would be 3 volts, right? So right here is my 0 volt ground. So measure against the ground plane someplace. Right here next to the switch. And if I'm measuring 3 volts at that switch, when I depress the switch, that means that usually I have a bad switch. It's not connecting inside. But then you measure to the other side of the switch. So if you measure from here to here and you have 3 volts, that means that your switch is bad, right? So digital circuitry is looking for a ground or negative and an active low. A lot of people think that you should be expecting 3 volts and, well, that means my button's being pressed. No, 3 volts on digital circuitry usually means that you're not getting the input that you need. So you can see this right here is kind of how it would look if you use my ground plane as a reference. This is an oversimplified version, and this is a video controller board. So yes, it's a little bit different, but the video controller board is got the same type of ground plane. You can see it all around the edges. And these buttons can easily, instead of running 2 conductors all the way over, what they can do is tap into the local ground plane, and you have really short traces for ground. Now, why? Why do you think they're using ground instead of a positive? Well, let's say this circuit board right here is next to a power transformer. I've got a power transformer right there. Let's say they're really close to each other, or let's say some liquid spills in here, and I get, let's say this is not tied to ground, okay? And let's say some liquid spills in here, but this circuit right here that's connecting all these buttons is a positive 3 volts. Well, if the liquid gets in there and it spills all over the place, then 3 volts is going to be going everywhere, right? But on a circuit board, if liquid spills in and they're all ground triggered, then the whole board is probably going to short circuit and go 0. And just the same, if there's noise from like a transformer or something and it creates a spike, it creates noise. Well, as I said before, noise does not do so well on a ground plane. In fact, it disappears. But if this is a positive plane and it's looking for a positive pulse to confirm a button press, then a little bit of noise next to that circuit board would actually trigger a false positive. So this chip right here gets positive 3 volts. 3 volts is nothing, guys. So it gets a little positive pulse, 3 volts, and it thinks you pushed a button. Now all of a sudden this guy's starting to trigger and it's starting to run a motor and stuff because you put two circuit boards too close to each other. Now it's impossible. It's absolutely impossible to get a false positive with a negative trigger because the negative trigger is nothing. It's nothing. It's zero. So if anything, if this all zeroed out, then your chip would also lose its VCC and it would not activate. It would just lose everything and it would go to zero. It would shut off. So, but a positive 3 volts to any of these pins, that could be detrimental. And it can be simulated with RF frequencies, things like your cell phone. You can set your cell phone next to a circuit board, and with an oscilloscope, you can actually see waveforms happening there. Now, God forbid you do something even crazier, like a Bluetooth speaker or some sort of audio device next to a circuit board. And you will see some of the waveforms generated by the amplifier and the switching. It will activate on the board. That's why boards like these will have extra shielding near RF componentry so they don't activate on other sections of the board. But that's why we have active low, is because it's less susceptible to noise. It creates easier wiring paths because we already have a ground plane. It's everywhere. So we don't need to run positive wires for each and every one of the little buttons. We have a ground plane. It exists. And the chips have been using active low circuitry for decades now. So from now on, if you want to measure a button, and almost all buttons nowadays that interface with any sort of circuit board are going to be a digital circuit. You should measure it first to make sure you have your positive 3 volts, because that confirms that your chip is good or bad. When you press the button, this guy here needs to go to 0 volts. If it doesn't go to 0 volts, you have a problem. Now, remember, you can also put your meter in continuity mode. That's the little speaker. And you can have somebody help you with this. Put your meter leads on both sides of the button and then have somebody push the button, and you should hear a continuity beep. And that confirms that your button has actually got good conductive surfaces. Now, I did a whole nother video on restoring those conductive surfaces. It is entirely possible that those are defective, especially since those type of surfaces are susceptible to fluid damage. So, folks, from now on, when you go to measure buttons and interlocks and stuff, if it's a digital signal, expect it to have a negative on the pin, and that confirms that it's a button press. That's called an active low. Thanks for watching, guys. A little quick video on digital circuitry. Hope you found this interesting. I know it's a little winded, but we're explaining some pretty complex things here, and I hope you appreciate these kind of lecture videos. Thanks for watching, guys.
I'm here to assist you with all your test equipment needs, from multimeters and test weights to patient simulators and X-ray analyzers. If you need guidance or you have any questions, please don't hesitate to write me at jbarber@bcgroupinternational.com.